We're going to be talking now about fixed effects models and also multi-level models. Fixed effects model is what we've been doing so far. It's a new term, but it applies to all of the different regression types that we've been doing so far. Because what happens with a fixed effect is we have theta here. In this case, I'm looking at an equation where we assume that our observed values, our sample points, this is g in this case, is going to be equal to some variable, some set of parameters and variables, and then it's going to have some error in it. So this might be a linear regression where this is the slope and the intercept, and then we have our error. So in other words, we assume that there's this one set of parameters that's driving the nature of the system. And from that, we can predict what we think the value of our samples are going to be, or the observed effect. But there's going to be some difference between that and the real values that we collect in the field. And that's going to be the error or the residuals. So this is what we've been looking at so far, just defined a little bit differently. And again, we have our theta, which could be our slope and our intercept. And then we have some error residuals, changing that from our sampled or observed values. Now, the problem with this comes in when we start to group things over time. In other words, if we have a data set that we collected over different months of the year, or different seasons, or different species, or a classic problem here is one based on student performance. And these can also have multiple spatial scales. In other words, if we have zebras and wildebeest, there might be different things going on between the zebras and the wildebeest in one data set. So again, classic example where we might have a linear regression that predicts test scores based on income in a large area. However, within a class, the scores might vary based on a student's income, but within a school, they might vary based on the teachers. In other words, who's teaching in the different classes. Within a district, the scores might vary based on the property value around the school, because schools in the United States, K through 12, are largely funded by county property taxes. And so that would be an interesting thing to look at. But with our traditional tools, of course, we can't really group by these. We can't see this. Instead, our traditional tools would just blur out those effects and would actually move it into the residuals. Multi-level models have multiple levels. And this is where the coefficients of one level of the model become the dependent variable of the second level of the model. In other words, the coefficients of one level are actually created from another level, or predicted from another level, or another set of equations. So another way to say it is the first level groups the data, and the second level models the coefficients between the groups. These are also known as hierarchical models, nested models, random effects models, and also mixed effects models. So the idea being that if we have a traditional linear regression, like this one, y equals beta 0 being our intercept, beta 1 being our slope, times a coefficient, or sorry, a covariate, and then some error factor. That's all hopefully real familiar. What should be new is the J's, and the J's identify the group. So now we have another thing there where you could think of these actually being multiple equations. So instead of one linear regression equation, we actually have multiple, where the J's vary the different elements of the linear regression, especially the betas, our coefficients, and the error terms. And if you look down below, you'll see beta 0 sub 0j is the intercept for group J, beta 1 sub j is the slope for group J, and then EI sub j is a random error for individual observations, but again, in each group. Okay, so at level 2, then we're going to have equations that for any given j provide us with those coefficients. So now we have our coefficients are no longer fixed, they're now random variables, as in random variable that is based on a trend but with some random component. So they change. They're dependent upon their own set of intercepts and other coefficients. So you'll see down below that y00 being the mean of all intercepts. So in other words, we'll have this one equation that creates our beta zeros the y00 is going to be the mean of all the intercepts, so the average of all the intercepts. Y01 is going to be the overall slope at level 2, but then W sub j changes the slope. So the slope of the equation that predicts our intercepts at level 2 is then used in level 1 as a coefficient. So that's where the multi-level or hierarchical nature of it comes in. And then the same thing is true for the errors. And then here's our intercept equation for our intercept. Okay, and when we look at this graphically, what this is showing is that we have our first level, which again looks like our traditional linear regression, except it's got those j's in it. But then we have our level 2, where the coefficients are predicted based on another set of equations. And so that's where we get 2 levels. And again, usually this is only done at 2 levels, but it can be done at more than that. So at level 1, slopes and intercepts in each group have the same value or non-randomly varying. The slopes and intercepts at level 1 can either have the same value, or they can be randomly varying, or they can be randomly varying. In other words, they can vary based on a predictor, or they can vary based on an equation. Okay, so this brings us then to the random effects model. So now we have these multiple sources of error. In other words, now instead of our theta or model coefficients or parameters being fixed, they have some distribution. And this is why these are called random effects, because they have some distribution about them. So there's a mean and a standard deviation they get drawn from. Okay, and then there's also this variance between each group, or instead of having a theta down here that's fixed, we now have theta that is changing from one group to the other. And now we can see that there's a large random effect here, but by moving these thetas into each of the groups and predicting them as different values, that should reduce our overall error, because we're taking into account the variance between the different groups, or how the trends change within each group. So another example would be modeling the age of herbivores. If our sample includes both wildebeest and zebras, well, we might want to combine those because we get more predictive power, more data. But they could, predictor could be forage quality. The overall average is going to be based on all populations, but the wildebeest and zebra are going to have a little different behavior. So we'd want to model that with a 2-level. Okay, so just another potential example of natural resources. This is where mixed models comes in, and this is really what folks have moved to. This is pretty heavily used now. It's not used as often as the base methods because it's not needed as much, but when you're faced with issues where you've got these groups, this is where they come in and are really important. Mixed models refers to having both fixed and random effects. In other words, when you run a mixed model, the software will pick and say, oh, well, this coefficient can be fixed. Wait, this one needs to be predicted based on a second level. And you actually tell it to do that, but then you can see what the final distribution looks like to see if it's really fixed or not. So in a fixed model, the only random effect is sampling error. In a random model, the explanatory variables are random variables, and the effect is not correlated to the response. In other words, we need to break it up, okay, to see the correlation. So these are known as mixed effects models as well. It's another term you'll see them under. The assumptions for these is that within each group, the same assumptions hold, because we're doing traditional regression with this. The assumptions for linear regression or GLMs or GAMs all hold with linear area, homoscedasticity, residuals normally distributed, or whatever their assumptions are within each group. Once the observations are grouped, those assumptions can vary between each group. Okay, so the idea is the groups are more alike than between the groups, and they can have, one group can have one distribution to its residuals, but another group can have a different distribution to its residuals, and that's okay. These are all available within R, the linear mixed models, generalized linear mixed models, and generalized additive mixed models. These all, for the GAM, it treats the smoothing functions as coefficients in a second level model. So your curves, the smoothing functions for your curves, are actually created by another model. This creates a really powerful set of tools to be able to attack a whole bunch of different data sets. Very cool stuff. And it's all available in R. So there's different packages. There's quite a few out there. These are the ones that I've worked with in the past. But as you saw, Leon presented a different one. So yeah, you'll have to dig around, and I would recommend going through the literature within your own discipline and see what they use.